which Ian was asking me, I've seen a lot of bits and, I sort of understand each thing, but then how does this stuff actually start sort of coming together, and why do we have to learn all these bits? We learned how to mix fluids, we learned about fluid properties, we learned about matrix properties, we learned how to laminate mix, and how does this all work together? Well, in the end, we want to go and predict seismic reflectivity, right? Because that's what we're going and seeing in the seismic data. And the short answer is we need all those things to be able to calculate it. And let's start simple, okay? And the standard amplitude risking that most of us do is based on this model, okay? It's a half space. It's a half space with normally shale on top and a sand shale mixture with a fluid below it. And we ask, what is the reflection coefficient from this model, okay? Now when it comes to volumes, we make it more complex. I'll show you, we add another shale underneath it. That's the same as the shale on top, okay? But in terms of phase one, that is the model that we end up using, okay? And always sort of keep this in mind, because again, it's your assumptions that can be violated and cause you problems, okay? Let's just go and get to, what is the reflection from one of these interfaces, and also the particular reflection as a function of the angle, okay, of the reflection. So we're going to make it a little bit more complicated now. We're not only going to have that normal incidence thing that David talked about in his first lecture, but we're going to allow it to be at an angle, okay? And the approximation that we end up using ends up being a fairly simple approximation. It is a linear approximation in the contrast in terms of the change in the VP, VS, and density across the interface. It also only has the leading order dependency in angle of incidence. That leading order is second order, so you have a constant, and the first thing that comes in is second order. It comes in as sine squared, but if you linearize that, that's just going to be theta squared. And where again, theta is going to be the angle of incidence. Now, the particular reflection coefficient that's at zero angle of incidence, where it's going to be, if we go and ignore this, is a linearization. You can see that because it's just first order in the deltas of both density and VP. And normally you say, well, this should be the change in the acoustic impedance, which is going to be delta rho V over rho V. Well, if you expand that out, it's actually V times delta rho plus rho times delta V. Divide by rho V, and this is the linear leading order terms in that particular expansion. And because of that, there's also the factor of 2 that comes about in the denominator that Dave showed the other day. But you can see that this again is explicitly leading order in both density plus the leading order linear in the compressional velocity. Well, another thing to notice here is that one thing does not occur in this term, which is the shear delta Vs, or the shear velocity. The normal incidence reflectivity has no information with respect to the shear properties. The shear properties come in terms of the way things change as an angle of incidence here, okay? So that you need to go and have a reflection at some angle in order to be able to tell something about the shear properties. And that's what Dave is going to be talking about when you ask why do you care about AVO, that sometimes it can help you discriminate things in terms of the shear properties that you could not discriminate just in terms of the elastic properties alone, okay? Okay, and then many times, if you come from other companies, this is called L, okay? This is called M, okay? This is the intercept and slope, and those of you with mathematical background probably realize why they call these L and M. There's standard mathematical, sort of labels for that. Other people may even call these A and B, okay? And another thing that I want to go and point out is that this particular B that we put in there, and that it actually is a representation of the fact that theoretically B should equal 1. But one thing that you do, and we'll talk quite a bit about this, is that if you go and let's say have anisotropy, the simple sort of calculated angle of incidence ends up not being the true angle of incidence if you have some anisotropy in the wrong. And so you may see that the naively calculated angle of incidence can be different than what the effective angle of incidence is. So we put in a particular sort of correction factor, and I'll talk a lot about that in terms of calibration of AVO or this relationship as we go on. But theoretically, B should be 1, okay? And also, this particular theoretical angle is nothing more than, if you know the sort of the velocity of the stack, which is at root mean squared, what time the reflector is at, and sort of the mean squared sort of offset from where the receiver and the transmitter were on the surface, that is really what defines this sort of theoretical angle that you end up having according to this expression, okay? And so we end up having small angle, small contrast, and we only keep the linear terms, okay? And a couple things I want to sort of tell you, though, as you go out into the more general literature that may sort of start confusing you. Okay. There are many different approximations out there. They all have their own names. There's a good little, I think, sort of cottage industry in making your own approximations to this, okay? Aki, Richards, it goes on in terms of the different approximations people make, okay? And be very careful, and the one thing that confused me when I got into the game was I came into it as a physicist, okay, what's your expansion parameters? Let's keep leading order in your expansion parameters and truncate anything of higher order. Well, if you go and take a look at a lot of these expressions and try to make them equal to each other, they don't, okay? And the reason why they don't is they keep arbitrary sort of second and third order terms. They don't keep them all, they only keep part of them, okay? And they all keep different parts of them, okay? And that's the reason, so they say don't be confused when you go out and start to see this, or start asking what are sort of the similarities and sort of differences between them. Another particular comment I want to make is a lot of people go and ask, why don't you use Zoppritz, okay? Zoppritz ends up being sort of the full-blown, infinite half space, sort of ray path solution to this, okay? And this is probably more of a thing for aficionados, but what you really need to know at your level is that this ends up being many times much better than the full Zoppritz, okay? And that probably you'll go and say, that's very surprising. Why would that be the case? Well, you have to understand that the approximation in Zoppritz is that the wavelength is very small in comparison to what you're reflecting from, okay? And it turns out in many cases, and Dave showed this, that's not the case, that you actually are averaging over the seismic wavelength. And what matters is sort of what the average is in a seismic wavelength above that package and what the average is in a seismic wavelength below that package, okay? And what's nice about this is there's a nice symmetry to this particular expression, or it actually renormalizes well. That if you go and have a particular, top and base of a package, you'll find that you get sort of the opposite response at the base that you get at the top, and things cancel out nicely. If you look at Zoppritz, there's an asymmetry. And you say, well, what's the difference, okay? Let me sort of tell you, say we had one little thick, really, really hard carbonate that was about 1 centimeter thick, okay? And we put that in, a really nice soft shale background. If you did a layer by layer reflectivity, you'd find the wave goes into that hard one. It's above critical angle, probably, and immediately never gets to the base. It never goes through to the base, okay? Is that right? No. What happens is the wave averages over that little small hard thing and goes right through it, okay? And so that particular expression, or the Zoppritz expression, ends up giving you the wrong answer because it's not renormalizing correctly. Another time, and it's very closely related to this, that you'll see there are significant deviations, is when you have many small thin beds. And it's also well known that Zoppritz can start breaking down in that particular case too, but it's related to its renormalization properties. And so again, this particular expression, what you need to know practically is, hey, you're using this real simple expression, yes, but it actually goes and functions much better than the more complicated expression, okay? And so, I mean, I've gone through that and talked quite a bit, but as I've gone through, my experience has been that this is something that really is surprising to people, and they sort of always have questioned why we've been and used something as simple as what we have up here. Okay? Any questions that people have? Or?
So if you go to the next order and include the second order terms, do you preserve your renormalization behavior?
No, because I think you lose some of the particular cancellation symmetry, I think. It'd be interesting. We can have some offline discussions about it. Yeah, but again, it's fairly profound on that.
Yeah, just on that, Mike, I suppose there's cases where we really do want to model out to 50 degrees, and that's probably not that great to get out to those sorts of angles. And I suppose if you have got a fairly thick sand that is, reasonably, it's got a reasonably uniform geology above and below, it's probably the way is to use Zoppritz, or alternatively, if you're aware, we can go to using
Full wave Kennen.
Yeah.
I would highly suggest that you use full wave Kennen. I mean, modern computers are darn fast. I would skip over it and go to full wave, in those particular cases. Some of the particular large angle behavior on the beginning of some of the hockey sticks can be absorbed by sort of a refit of that slope though too, and that actually can compensate for it. I would go and say, if you're going to go to anything more complicated than this, go immediately up to a Kennen-like solution, which is a full wave solution and will give you, I think, a better result. And again, there's no reason not to do that. Okay, now I'm going to go through the particular procedure of how we actually generate one of the, what I sort of call these hump plots, or these sort of stochastic diagrams. And I'll show you what they look like right after this. When we talk about the procedure, and I think, Ian, you'll find this starts stringing everything together. Like, and we didn't give you any beads you don't need. You'll find you have no beads left over once we get them all strung together. First of all, we generate the end member sand and shale properties, and we do this as a brine sand, or a reference brine sand, and we do it. First of all, we choose a random LFIV and depth below mud line with whatever uncertainty we have. If you feel I know the imaging velocity within 100 meters per second, that's the uncertainty we pick this with. And we pick it around a mean with a standard deviation. Normally you know the depth quite well. Okay, but there could be some depth conversion uncertainty that you have. We substitute the exact value we picked at random into the VP sand and shale trends to generate the most likely VP values, okay? So remember we had that equation for VP that I just showed you. We substitute these, we spin the roulette wheel, we pick a value of these two, we substitute these in here and we get a most likely VP. We know that that expression has some uncertainty around it, so we spin the roulette wheel again and choose a VP around this most likely value with the uncertainty. Then we substitute this VP we've just chosen into both the VP-VS trends in these cases, and those will give us a most likely VS, but we know there's an uncertainty in that, so we spin the wheel again and come up with random VS's. We substitute those VPs again into the porosity VP and the density VP, spin the roulette wheel, and get one of these porosity and shales, okay? So we've used the last part, once we go and have what the VP, VS, and density are of both the shale above as well as that laminated mixture, we can then go and form what the reflection coefficient is, both for normal incidence or a near stat, or a larger angle of incidence, or what we normally call a far stat, okay, using this formula. So there's the last one of the beads that we ended up using that we talked about. And so then what do we get in the end, okay? That we get for the particular shale versus shale reflector, where we have a shale on the top and a shale as the second one, we get a mean of 0 because we assume that both shales are about the same. But you see that there is some fluctuation in the way that we expect the shales to look in terms of their end member. So we can get both positive and negative reflection coefficients probably out with an RMS of about 2.5 to 3%. In fact, if you take a look at, you're talking about Hess and where they really like to, you have defined their background according to shale. It really is according to the width of this that they tend to go and try to reference everything. Okay. Then you can see that the brine on average is a negative reflection coefficient about here with about 4%. It could get as small as being transparent or about as large as 7%. The oil is shifted over a bit more and is sitting over here at about 6%. You can see how large and small that can get. And the same thing for the gas case, okay? And we also, you'll hear us call these, the technical word hump plots because they look like humps, okay? And we also have another way of showing that. I think it was Guy, I think you even were the first one, I think, to show this, I think, of taking these and saying what is the mean and standard deviation and showing it just as simple bars with error bars on it. But that's just literally like turned sideways, showing you where those sort of Gaussian distributions are, and also assumes that it's Gaussian to be able to do that. The one thing that you can already see, and this is where you'll go and sometimes be surprised, is that someone will say, hey, look, I have a reserved amplitude, I've done everything normalized at the shale, and I see I have about a 6 or 7% reflection coefficient sitting right here. Wow, that's really close to what I think oil is. I drill it, and it's a really good brine sand, okay? And I think that you already can see that that's something you should not have been surprised at, because if you looked at, and we were looking at how good a brine sand can be, you can see at this reflection coefficient, it could equally be the same as both, okay? And so already you're starting to see some of the advantage of not just saying, this is what a brine sand looks like, this is what an oil sand looks like, but we want to go and understand what is the range of what those sands look like, and can we confuse a failure case, like a shale, with an oil sand, okay? I mean, you could have a little bit be a below average quality oil sand at 5%, and that might just be an exceptional shale, for instance, okay?
How do you narrow the
You're going to go and answer that question in the exercise. But to give you a bit, what we do, okay, there are obviously a lot of random numbers we grab, right? And you don't know which one of those is most important, right? Well, you can go and look at and have a standard sensitivity tornado chart to ask which one of the inputs is influencing the output. And we actually will show a ranked seriatim of those. And you can see which is the dominant effect on determining the uncertainty and the reflectivity. So, but you'll be doing that in the exercise.
That's the one to work.
And it's a very important, it's I think a major value of this, because a lot of times people say there are a lot of numbers that go in this. Which ones should I focus on? And I always sort of say Lyndon Johnson, the U.S. president, when it came to the Gulf of Tonkin resolution, people asked him, what was that like? He said, it's like my grandmother's nightshirt. It covers anything, And he really meant it that he could really do whatever he wanted to in Vietnam because it really didn't give him any restrictions. But my particular philosophy is to sort of use your grandmother's nightshirt. When you go and look at each one of these uncertainties, make sure the uncertainty is big enough to really cover anything, or if you ever err on having the uncertainties too large, you do your sensitivity analysis, and then you go and ask, what's the important thing, and start going and using that as your work program, okay? And when you find that you hit something that's dominant, and for some reason the Earth is just not kind, and that is the natural variation of the rocks, period, there's nothing you can do, that's a particular point that you end up saying, I just have to stop work and not continue on worrying about this other large number of things, okay? And so it's a nice way to be able to dose your work. And so asking the question that you asked there is very important in terms of making sure you don't do a lot of extra work that you don't have to do. Okay, I'll turn over the floor to Dave, and he'll talk a little bit more about sort of background on seismic reflectivity.
Is this still lecturing?
Mike, there's a little white. Here's all.
Oh, no, I probably carried it away. I don't know. What? Is it there?
Yeah.
Oh, no.
Oh, I'll just use it. It's just here. Good, thank you. Okay. We keep talking about reflectivities. I should have a logic chart here. We're going to calculate reflectivities, we're using trend curves, we're going to compare them, we know that logic chart. Now we're going to start talking a little bit about that first leg up on the top, which says, I got to get those seismic amplitudes measured somehow and calibrated. And that's what the next several view graphs are about. So I want to start with the way seismic is done and some things you should always remember when you're dealing with it. What you see normally in seismic will be a record, which just looks like a bunch of squiggly lines down, in time, and then you have different positions along the Earth, so different traces as you move along, a profile, if you like. And if you have a 3D survey, you'll have a whole sequence of profiles, and you can page through them if you like. Think about one of those traces and what it is first. First of all, I'm not going to get into, imagine that you simply have a source and a receiver at the same point on the Earth. And you ping the source off, and so what is it? It's a point source, and it radiates energy in the hemisphere. We're not even going to worry about energy coming up into the atmosphere. We can take care of that. So think of drilling a hole, putting a dynamite charge down there, which is what we used to do, and go bang. What have you got? You got a point source that radiates energy out, acoustic energy out in the hemisphere. What's the amplitude of the signal going to look like at some distance away from you in the Earth? That's the kind of question you might ask. And that's what this thing's about. The amplitude at some frequency in the source bandwidth, and at some time, not distance, but we could talk about that in a minute, it will be the source strength A0 times 1 over T. What's 1 over T take care of? Well, we're talking amplitude, so the energy is going to spread over a surface of a sphere. What's the area of a sphere? 4 pi r squared. So 4 pi r squared. So it goes as r squared, and we know that the energy goes as the amplitude squared. So the amplitude is going to go as r, 1 over r, right? So for a constant velocity medium, 1 over t will be how things will change with time. You have 1 over r with that constant velocity, so that's what you get. Your constant velocity being 0. But of course, the velocities increase in rocks, typically, as you go down in depth. We've been talking about compaction, particularly in soft basins. So in fact, instead of having a bunch of straight rays, if you were to draw the ray paths, they actually bend away from the normal, and the sphere gets ever bigger as you go away from the source. So you have another term, which is this increased bending due to the increase in the velocity function with depth or distance from the source. So for small angles, reasonably small angles, you could write something like this, where VE is the effective velocity, the RMS velocity, the move-out velocity, in essence, from the seismic data. This number is bigger than this number, so you've got an extra added term, and it goes like the square of the ratio of those velocities, that increase in the surface area that you're spreading the energy over. So far, we haven't lost any energy. We're traveling through a homogeneous medium, and all we're doing, and it's a lossless medium, all we're doing is spreading the energy. Right? So we haven't lost any frequencies of any frequencies that were in the source, they're still there, et cetera. Now, but the Earth isn't like that. After all, what have we been talking about all this time? We've been talking about contrasts in rho v, which give us reflections. Okay, so some of the energy at each one of those interfaces, geologic interfaces where you have a contrast in acoustic impedance, some of the energy comes back up to the surface, and the rest of it goes through. And then you hit another boundary, and again, some more comes back up. And when it comes back up, there are layers that could send more of it back down, so it gets delayed. It gets very complicated. It gets very complicated what you will see back at the surface, at your receiver back at the surface. This term is meant to take care of that diversion of energy from the beam by scattering. That's what that really is. And it is a frequency-dependent as well as time-dependent effect. And if you look at a lot of synthetics and calculate based on logs how this baby behaves. By the way, I should have said this loss is not logarithmic, so you can't say. But when you get fairly, in the far field, it's approximately like that. It'd be about 6 dB per second of two-way time of loss of energy. Everybody familiar with dB? Talking on dB. 20 dB would be a factor of 10 in amplitude. 6 dB is a factor of 2 in amplitude. This is a logarithmic scale. This guy is maybe another 2 dB per second. This guy here is 2 dB per second, but it attenuates the higher frequencies more than the low frequencies. So you start to lose high frequencies from the source that you're not going to retrieve when they get back. They get smeared out. The returns get smeared out, and that has the effect of canceling the high frequencies more than the low frequencies. Just sort of like when you get my age, you won't hear as well with the high frequency end of the spectrum. Okay, so now we've got what? 6, 8, 10 dB per second. Then there's this other term over here, e to the minus alpha ft. What's that? Well, the Earth isn't lossless. Some of the energy, what you're doing is you're moving particles, either longitudinally for a P wave or transverse. To move particles takes energy. And some of that energy, you don't recover when the wave passes. It's converted into heat. There's friction. So you lose energy when the wave passes, just as it's propagating. And that loss in a homogeneous medium is well described by an exponential, inverse exponential, alpha being the loss coefficient that's proportional, the loss is proportional to frequency and to the distance traveled, which is the t bar. So alpha is about point, I don't know, it can vary, but in a seismic band, it's like 0.25, something like that. 0.25 dB per cycle per second, so 2 dB per cycle. And so this baby's another 6 dB or so per second. So now what did we say? We had, what did I say? We had 6, 8, 10, 15 or 16 dB per second is not an uncommon loss in seismic energy. So now, what do? I go down, how many seconds are we talking about? Well, if I'm prospecting, let's say, 10,000 feet, I go down 2 miles, I come back up 2 miles, that's 20,000 feet. My velocities, on the average, were 6,500 feet per second or something. I've got a reflector at 3 seconds on my seismic record. It's lost from the source, from the energy that was generated at the source. It's lost what? 45 or 50 dB of energy. What is that? Well, let's see, 20 was a factor of 10, 40 is a factor of 100, 50 is a factor of 300. So it's 1/300 the strength of the signal that left the source before it gets to the reflector. And then I told you the reflection coefficient for a normal brine sand interface is like, 0.05 to 0.1. Let's be generous. Let's make it a 0.1. That's another 10 dB, right? 20 dB. Sorry, 20 dB. Factor of 10. So now we're down to 3,000. 1/3000th of the energy in the source is what's coming back. That signal is really weak. So you're familiar with this when if you have a little handheld microphone, it has an automatic gain ranger, so that if I'm close and I talk at that thing, and then we play the tape, you'll hear it. But if I keep my mouth shut and there's a choir singing over there 100 feet away, you'll hear the choir, even though that signal is a lot weaker than my voice, because it'll automatically range gain up because it was quiet in between. And so it's got to boost the gain until the next signal comes in. Well, that has been a common way that seismic data are handled in the amplifier. The seismic recording instruments have an amplifier in them, and they automatically gain range in order to adjust the signal strength. So when you see this trace that just has a bunch of wiggles, it's already been gained back up, so that those very weak signals that very rapidly in time look pretty much the same. And that is why you see much more coherent events on your shallow record. That Falklands data that Mike just showed you looked very nice. You saw those nice reflector events at the top. If you got down deeper, as you get down deeper in any record you look at, it's going to get hashier and hashier. You're not going to see nice coherent events so easily that bop along and you can easily correlate it back. And why is that? Because the signal is getting weaker and weaker. Eventually it drops into the noise of the background noise of the seismic amplifier if you go that far. So what we always have to do is to try to recover. You have to gain the data in order to recover this signal character, if you like. And you can automatically gain range, but if you do that, you have no way of relating the reflector strength, the reflectivity strength at, say, 3 seconds to the reflector strength at 2 seconds, unless you can recover the gain function that you applied. That would take that you have to record it, and there were instruments built that way, that you recorded the gain factor that was being determined every 200 milliseconds. That's not commonly done. Instead, what you might do is to go back, and this is a much better kind of procedure, and say, I don't know what these things are, but I'm going to take a gain function that has a form like this, a deterministic form like this, and I'm going to stick in these things. I may smooth them laterally in spatial coordinates, etc., to try to make it less, nervous. But I'm going to smooth these things, and I'm going to put in the values that I determined for my seismic data, and some values here, and we'll just let this thing. We won't worry about that too much. The frequency dependence, and I'm just going to put a scalar function of that type I'm going to restore the level of these signals with a scalar function of that type. So this is the kind of thing you might see. Here's my actual RMS voltage that I recorded. It's been smoothed. And here's the decay curve of the proper functional form. My trace really went like this, right? Big things like a galvanometer, and gradually, so now I boosted all those things back up. And these things are the significant events. Okay? They can be negative or positive, but they are the significant events. Okay, so now we have a band-limited seismic trait. We're going to come to that. Next thing I'm going to talk about is calibration a little bit. And calibration goes like this. I have a wireline log. What's my problem? I have some numbers on a tape when I get my seismic data. I don't know what those numbers mean. They're somehow related to the millivolts response in my seismometer. Okay? And that, in turn, is determined by how violently the Earth shook as the signal hit the seismometer. But I have applied a gain function and jumped them up, and I don't really know what that means anymore, even electrically in most cases. In certain cases, you should know what they are in millivolts, but it still doesn't tell you anything. But I can do this. I can take my wireline log, and I'm going to do things in the run-sum mode that we talked about earlier. I have a density log, I have a velocity log. I'll take the product of those two logs, take the logarithm of it, and here's what it looks like. My log, of course, I have units to these things, grams per cubic centimeter, centimeters per second, or whatever you want. Right? So I know the units of this log. And it increases with depth because of the compaction. So in other words, it has a very low frequency as well as a DC. But I know what the units are. So the next thing I do is say, well, my seismic data doesn't have DC. It only has a certain bandwidth of signal. So I don't have a DC, let's say it goes from 10 to 50 hertz or something like that. I can tell that by looking at the coherence of one trace to another, what the seismic bandwidth is. You can take spectra really easy to trace, look at how they fall. So now I say, look, I've got this wireline log, and it's got very high frequencies. Of course, the logs are measured in depth, but I have a velocity function. So I know velocity is a function of depth, so I can convert the log to time. So I know how to do that transformation. So now I've got a log rho v in time, and I can band limit it. Here it is band limited. And now you notice that I put some numbers on certain bumps in the log before it was band limited, and then they get sort of smoothed out to get the seismic bandwidth. You saw that slide earlier this morning where I was talking about the seismic trace over there and talking about what the log scale was over here, and it was so much finer. This is a cartoon, but it would be smoothed to much more than this. But these bumps are still going to be here. These are big bumps. I label those bumps, and I have an integrated seismic trace at the well where I recorded the wireline logs. Okay? I did that run sum. And I removed the low frequencies from that run sum. So I now have matched bandwidth of a wireline log of the acoustic impedance log of the acoustic impedance. And on the seismic trace, tape units or millivolts or whatever I know about the seismic trace. And if they correlate, and they should correlate, otherwise these things that I'm seeing on the seismic aren't really coherent events, or if they are coherent events, there's something wrong with the log measurements at that particular time, right? Because they should match. And I can take and plot 5 against 5 and 6 against 6, whatever. Just like this. Here's my field seismic, it's in millivolts. Here's my synthetic seismic. I measure that amplitude of the 5, can be positive or negative. I can measure the amplitude of 6, it's negative. And I can draw my best fit line through the origin, through those two. And that gives me a calibration in terms of log rho v units, right? In terms of how many millivolts is it for a gram per cubic centimeter times a kilofoot per second, or whatever the heck it is. I can get that correspondence. So that's how we would calibrate a normal incidence trace. And this shows a comparison between some synthetic and some seismic traces at the well. Now, you heard me talk before. This is, we never show typical examples. I have to say this is a very good example. Quite frequently, the correspondence isn't this good. Okay. But you do see this. This is what to look for in synthetics, and I've talked about synthetics a little bit before. It's a very important tool. Excuse me, Mike will talk about it more later. He talks about wave of derivation and inversion, but this is a coherent event, right? You see it. This is a coherent event. In fact, all these are coherent events, and this data is very good. So if the log does not match the seismic at the well, that's a problem. I talked about it when we were talking about quality control and trend curves. And said, where you have this log, if you have seismic data, you should look at the correspondence between the seismic and the synthetic. And at any point in the law, in the well log, where you have a coherent seismic event and you're not matching that seismic event very well with the log, you should worry about whether the log is representative of what the seismic is seeing and whether there might be an error in log measurement. It may not be so. It may be just stratigraphic variation. The seismic, you have to remember, at any one point, despite migration, is still looking at a very much larger piece of rock at depth than the log. The log has an investigation of something like a foot in radius beyond the borehole wall. The seismic, even after migration, has a radius of investigation of something like the spacing between traces. And again, that's what it's like. So that might be 25 to 50 feet. So it would be about the size of this room, Dr. Long. So it would be pretty easy for you to drill a hole 8 inches thick, that's as big, and you're looking at a zone as large as this around the borehole, and for that to be different than something that's an average over this whole room. Whatever the reason, you would say, well, I think I won't pick that one if I've got other things to do. There are other uses for the seismic. This is a nice one. Okay.
Yeah, it's probably time for a break.
You want a break here? Okay.
We're actually time for an exercise and
Okay.
sort of afternoon tea. So
Okay.
I sort of pointed out the thing in terms of normalizing to the shale. I think Dave, when he was just talking about that correlation of the well log to the actual seismic, is another way of actually getting things corrected to actual reflectivity units that you now can compare to actuals. So it's yet another method, and as I go through and we start talking about normalizations and get into exercise 5, a large portion that's going to be focused on how do we go and get that conversion, that millivolts to reflectivity units conversion that Dave was showing there. So.
It was lower than the P wave velocity. Okay, so it's going to come out bent toward the normal. Same thing in the lower medium. I get a P wave and a shear wave, and the shear wave is close to the normal than the P wave. So now I got 4 waves leaving the interface instead of 2. And these were some numbers that I put in just for this particular case. Zopret's equations tell you the amplitudes of these 4 waves with respect to the instant amplitude, just like that normal instance reflectivity coefficient was the reflection coefficient of the amplitude of the reflected wave at normal instance over the amplitude of the incident wave. So when we looked at this slide, and Mike showed you this slide, that's what this is all about. The reflection coefficient here is, this is an expansion, an approximation, but the Zopret's equations would tell you what that is exactly for a plane wave interface, plane wave incident. Okay, so now let's think a little bit about that. This is a case that we just showed. That is this case. These are reasonable numbers. I have a contrast in velocity. BP is bigger than the lower medium. I have a contrast in the shear wave velocity, 2, a bigger contrast, and the contrast and then there's a little contrast in density that's opposite to the contrast in velocity, in case you didn't notice. And So what happens? A normal instance, I have a P wave reflection, but damn, it's not very big. Maybe 0.02 reflection coefficient at the normal. And when I move out to 30 degrees, as I move out, 30 degrees, by the way, is a reasonable number for where you blank seismic data because of refraction levels, et cetera. So it's a pretty good estimate to the normal kind of data you would see to the angle range that you would have in that data. And here is P wave, and now it's positive. It crosses zero, and it's positive. So what am I going to see if I have a situation like this? And this might very well be a shale against the sand in some places. I'm going to see no reflection at all, because I'm summing this reflection coefficient if I got the right move-out velocity, and I get some positives and I get some negatives, and they cancel each other out. No event at that interface between one rock type and another rock type. Oh, that's not very good. I told you before that sometimes things aren't as nice as they were in that example from Brunei, where you could see down dip that reflect the top of the reservoir unit get weak when we went into the down dip portion where there was brine and no hydrocarbon. Remember that blue-red nice picture with the fluid interface reflection? But what about the reflected SV wave, the vertically polarized shear that we saw in that diagram? Well, that guy, of course, it has to start at zero at normal instance. There is no shear allowed. But as I move away from normal incidence, the amplitude of that thing grows, at least out to 30 degrees. But eventually it rolls over, it comes back. But it's a significant amplitude out here. So if I were to do shear wave prospecting, that is, look at the horizontal motion, first start with a source that did this, and then secondly have a bunch of receivers over here that were picking up this horizontal ground motion, I would see this guy. The normal detectors we use are vertical. And since they're at relatively small angles, they discriminate heavily against these waves, which are really there, even though they're offset, because you have what amounts to a sort of a weak but a fairly effective polarization filter. It just sort of suppresses this wave because it only has mostly horizontal motion, vertical motion. And you're only looking at the vertical motion in a normal P wave seismometer, vertical seismometer.
We're talking lands here.
Yes, talking land.
Yeah.
In marine,
Yeah.
you have to look at converted waves. So it can be done, but you need an ocean bottom seismometer or something, a cable or something of that nature, and that's been done. In any event, if you had the shear, if you were able to do shear prospecting, then you would see this reflection at this interface between the quote sand and shale or whatever. But so what are some of the consequences of the fact that you have these multiple waves? Well, one thing is obviously that thing that I was telling you about. When I integrate, instead of getting the normal incidence reflectivity of maybe minus 0.02, as we saw, I would get something that looked like zero if I integrated over 30 degrees. So what that means is my calibration doesn't work anymore, right? I just told you how you calibrate a normal incidence about an hour ago. That was, I'm going to take the log and I'm going to do the rho v, construct the rho v log, take the logarithm of that, and limit it, and then compare it against the seismic, and that's how I'm going to get my answers. Well, if I do that with a stacked trace, I could be messed up because the stacked trace might not correspond to the normal incidence reflection coefficient in the case like we just saw. So that's one possibility we have to worry about a little bit. Another one is detecting changes in the shear wave properties without having to shoot separate shear or converted wave seismic data by using amplitude versus offset or AVO analysis of compression wave data. Well, you already know that that's what we do now. For about 10 years, there was a great deal of activity in the industry in shooting shear wave data, both converted wave shear data, horizontally polarized shear data, etc. And some is still shot, but very little. It's expensive. And so people instead say, well, why is it that I get this way? I get this way because there's a partition of energy once I get off the normal instance. And so the partition of energy, that is, the magnitude of this wave is, the magnitude of this wave is telling me something about how much energy was pumped into the shear wave at the interface. I've lost energy into the shear wave, and it has an effect on the amplitude of the P wave. So I could just look at this guy again, like I've been doing all my life, only I now have to look at the behavior of this guy with offset, and that will tell me something about the shear wave properties. Now we're going to go backwards again to this equation. And one of the great benefits of this kind of equation, besides what Mike talked about an approximation that works appropriately at low frequency, you average properly, is that you have an understanding of what the property connection is to the behavior of this amplitude, of the reflection amplitude with offset. You get to relate that to the rock properties in some way. You have a functional character. This is our normal instance, our normal instance reflection coefficient we've been talking about up till now. And over here, this is this M term, which really tells you how that curvature in the P wave reflection coefficient relates to the shear properties. And I want you to pay close attention to one thing, because it's going to be very important in a moment. I've been sort of cluing this in the last day or so. You have a VP squared in the bottom here, and you have a VS squared in the top. So you have think of this as VS over VP squared here in this term. That's negative inside this whole bracket in this M term. That's a big term. So VP over VS, think of that squared in the denominator. Remember that. We're going to come back. We're going to use that in a moment. Okay, now let's just look at some realistic rock elastic properties for, a what if, a model kind of thing. So here's a case where I have a top medium. The top medium never changes. And it tells you what the numbers are here. All the properties are the same. 3 cases we're going to look at. The bottom medium has the same VP in each case, the same density in each case. All we're going to change is the shear wave velocity. Okay? So the normal instance reflection coefficient is never going to change for these 3 cases. So let's see how the AVO changes. By the way, these rock properties are chosen to be realistically capable of occurring at a clastic interface in a soft section. In other words, you could cook up any case you want, but if it doesn't have anything to do with rocks you may ever observe, what good is it? It would be pedantic only. This is not just pedantic, it is realistic. So here's my normal instance reflection coefficient. It's a 12% reflector. That's a nice one. And here are my 3 cases, 1, 2, 3. And you see that the M, that is the amount of curvature here of this P wave reflection coefficient varies. This is a separate solution. Varies with the 3 cases. It varies with the shear wave velocity. So it means that I should be able to extract something about the shear wave properties from that M coefficient. You saw Y in the expression that Mike had in that expansion. Just for completeness, here's what the SV looks like, 1, 2, 3. And if you were to take the ratios of these 3, let's say out here or even in there, you would find that they correspond to the ratios of the P wave reflectivity at offset 2. Here's the this is incident SV, reflected SV. For those of you interested in shear wave, shear wave prospecting, if you looked at the ratios of these 3 normal incidents, they would be the same as the ratios of these 3 at these offsets, at least out to the angles where this peaks. And then this would be what you would have if you had incident SH. What's SH? Suppose I shake this way and I record this way, so that when my disturbance gets down to the reflecting interface down here, the motion is all in this plane. There's no split up. So P waves cannot convert into SH waves, only into SV waves. So the SH is simpler, and you get a simpler behavior. And again, these three would have the same ratios as the SVs or the incident SV reflected, or incident P SV reflected. All right, so now let's think about M and L. I could plot each trace, instead of having one value on my amplitude curve, you know, my calibration curve. Remember that plot I made of seismic amplitudes versus log rho V's or something, I have one measurement, an amplitude at each time on the seismic trace. Now I don't have one measurement, I have two measurements. I have the reflection coefficient, that's this L, that's my old one measurement. And I have another measurement, the amount of curvature, if you like, on the P-wave reflection coefficient as a function of offset, M, the M coefficient. And what I find, so each point in the plane, suppose I pick a number of shale points, shales, I'll say, shale interfaces or shale siltstones or something like that. Each one of them will have an M and an L, and I'll plot it in this plane, and it'll fall someplace along there. Maybe I just drew a locus of points. That's what typically happens. They fall along some trajectory in this plane. And if I look at shale to brine sands, let's say, some of them might fall, they might be away from this locus of points, but they would fall in some other locus of points. And now I'm going to stop right here, and I'm going to go backwards again. I'm going to say, what's going to happen when I go back to this equation and I do a Gaussian substitution? There it is. I got this VP over VS in the denominator squared. What happens when I do a Gaussian substitution for light fluid, squeezable fluid, for stiff fluid, hydrocarbons for brine? The VP does what? Goes down, right? Somebody said decreases, didn't they? What about the shear? Shear wave increases, right? So VP over VS changes, and it drops, gets smaller, right? It always gets smaller when I put in the hydrocarbon fluid. So VP over VS gets smaller, VP over VS is in the denominator, means this term within the brackets gets bigger. But this term has a negative sign. So algebraically, M is going to get smaller. And we know that L is going to get a lot smaller. It's going to go negative, right? That's what happens. P-wave reflection gets smaller, bigger in magnitude, but smaller algebraically, negative, more negative. So let's go back now. Here we are with our brine. What's going to happen? What's going to happen to this sand against that shale while I put hydrocarbons in? L's going to get smaller, and M's going to get smaller. It's going to come down here somewhere, right? That's what's going to happen. What's going to happen to this one? It's going to go down here. So I'm going to get a new locus of points, and that locus of points necessarily will have to be displaced this direction. It might be that direction or this direction. But this direction, from whatever the locus of points is of the brine to sand reflections that I have plotted here. So let's look at that. There's a gas. It'll be somewhere down here. This guy went that way, went this way. Okay. So I can draw a line through here. These are my background events. And I can draw the normal to that line. And this is the shale that we're against. The brine sands will be displaced from these because they'll have slightly different VP to VS ratios too. And how much they'll be displaced depends upon where you are, what kind of rock properties you have in your basin. But that gas is always going to be away from this direction. So a common thing that's done with ADO is to look at normal to the background, however this plots, and look for those events which have the biggest values projected onto this normal in this space. Remember, I have two parameters at each time in my seismic trace. So if I were to take this and project this on the normal direction based upon these background events, that gives me one measurement from this plane for each time on the trace. And I can make a seismic display of that one measurement. And that seismic display is called a background normal display. And that background normal is intended to tell me something about where do I have big ABO effects, even when I can't see, maybe that could be related to hydrocarbons, even when I can't see the individual sand is there on a normal instance reflection trace or on a stacked reflection trace. Okay, I might still see a big ABO effect. You might say, well, why don't you just go ahead and calibrate the doggone thing like we did with the single measurement, like the DL alone. And it turns out there's a lot of flies in that ointment. I'm going to let Mike talk about that, but it turns out not to be that simple to calibrate, and thereby hangs a tale that Mike is going to tell you about next, about how he deals with this in the VHP bulletin methodology of VHP bulletin. I guess that's
And
what
before we move into that, you were going to talk about seismic data quality, AGC.
Oh, yeah, I completely forgot. That's right. I completely forgot about that, man. Good point. Cut this discussion and go back. I forgot to make a point that I wanted to make before when I was talking about the decay curves and the calibration, the whole calibration business. If you come into a new area and you suddenly get a big pile of new data that they say, here, we got the spec data, or we shot this survey, or we bought it from somebody, and say, we want to know if there's any hydrocarbons here or what have you. The first thing you should look at isn't the data. The first thing you should look at is that processing template that went with that data, the history of the processing of that data, because seismic data has multiple uses. And the first use everybody is going to make of it, they want to map events. They want to find out what the structure of things is, how the structures vary with depth, where the faults are, all those things. So the first thing you're going to get, you know that, pick coherent events and you map them. Processing is done in order to enhance one thing or another that you are interested in interpreting. The processing for enhancing the coherence of reflections, among other things, is a rapid gain ranging gain function. A rapid, what that's called automatic volume control, AVC for short, or AGC, automatic gain control. Like I was talking about the microphone, a very rapid change. They might have a window, they'll say on the side, gain in 2 or 3 different places. It's common to gain seismic sections if they were primarily intended for mapping. And they'll say AGC or AVC, and it will say, typically it will give you a window length. That is the response time that they are adjusting the gain parameters over. So it might be half a second, might be 100 mils, a very fast AGC. That way, if you have a fast AGC, when you get your record out, weaker seismic events still come out fairly strong, even if they're relatively close to stronger seismic events. They may look a little rattier, but you can follow them. So you get to see the character of the stratigraphy much better, and that's very useful in interpretation. So look at that processing template, first thing you do, and if you see AGCs, particularly short window AGCs, you better tell your boss, look, I'll do whatever you want me to do, but you're going to waste a lot of time if you have me try to look at this data for amplitude interpretation. We need to reprocess the data and properly handle the gains before we should attack it for all of this QI. I forgot to make that point, and it's an important point.
Mike,
Mm-hmm.
are we doing any of this perpendicular seismic displays?
When we perpendicular.
Well, I mean, it has to be called,
Background normal.
Jacques Levé called this perpendicular seismic.
Yeah, well, let me get to that.
Yeah, he's
It's
gonna
about what about ready to start talking about. So, and our take on it's probably a little bit different than what you probably have seen it at HASP, but is roughly equivalent to it. I'll talk about some of the reasons why we do it slightly differently. So, but we do the same effective thing. So, in terms of
is about way time to change, or
You got 4 minutes, I can make a new tape.
is it making a change?
Okay, so why don't you just hold them?
The spreading law varies with offset in a velocity, in a medium where the velocity is not constant. So there's a good reason to make an offset dependent gain and still try to retain the reflection amplitude character of the AVO. That doesn't mean that you can simply derive the gain function constant that Mike is talking about as a function of offset from the data and use that. But you may do that in processing. I don't know what's exactly done, but you could still follow the philosophy of trying to use a functional form that is guided by the way the physics works.
Yeah, I was just coming at it from the angle of below that gain control, really, the must effectively
Oh, yeah.
APO response.
Yes, absolutely.
Oh, yeah. I mean, it's
One of
so
the
much
reasons why
stuff up, it's really, and it's also data adaptive, so there's no way deterministic to take it out.
Yeah.
Type things that Mark is talking about, we know exactly what we applied, and you could take that out if you want, and also it's the same everywhere. So you're not going to create a spatial anomaly if you applied a spatial constant, is the philosophy. When it comes to the particular BHP style, you're going to find out that looking at the type things that we do, it's a different style than is done by a lot of other people in industry. In fact, you can even tell when Jock peeled off from Shell, because I'll be talking about a piece of research that actually postdated him, that's been presented in the open literature, that actually indicates there's sort of a different perk direction that you probably want to take. And I'll actually point you to that fairly critical paper that I think is really quite beautiful and really informs a lot of these choices. Okay? But first of all, let me sort of talk about there's the statement of when does AVO matter, okay? And that, well, there always is AVO, okay? But when do you need to go, and the question I like to pose, when do you need to have 2 reflection strengths rather than 1? Or when is, going and having near and far stacks better than having just a full stack, okay? Because if there's no reason to have 2 numbers, why do you separate this out and give up half of your stack power if there's not a reason to have that, okay? And let's go back to rock physics and how we answer the question of, are we going to want to be able to take a look at 2 numbers rather than 1 number in terms of reflection coefficients, okay? And the way that we like to look at this is not in terms of L and M, but in terms of near and far stacks. And I'll get to that in a second, why these are the coordinates. I will also show you that it's just a simple linear transformation between the 2, but it actually, there's another discriminating reason why you would want to do this. And so anyways, if you go and take a look at a soft sand case, normally what's called a type 3, okay, or a class 3 response. Why do they do that? Well, and why is it called a class 3? Well, it's fairly simple. This is the first, this is the first quadrant, second quadrant, third quadrant, fourth quadrant, okay? If you take a look at your predominant hydrocarbon sand, the blob right here is in the middle of the third quadrant, ergo it's called type 3, okay? It's fairly simple, and okay, where do you think a type 4 is? It's in that quadrant. Where's a type 2? It's in that quadrant, okay? It's very hard to get them over into the first quadrant, and so that's normally not talked about as such, okay? Okay, first of all, what is this, okay? This is what we call our shotgun plot, okay? There are 3 shotgun blasts, okay, or patterns on here. But each one is formed up, just as I talked about before, in terms of understanding the reflection coefficients. But now I'm plotting a point as one of the particular Monte Carlo simulations, and I'm showing where that is in terms of both near and far reflectivity rather than just say simply full stack reflectivity, okay? And if you go and see the way that things are set up here for this type 3, what we normally call a soft sand, and go and find out where are these shotgun blasts. So they're a little bit hard to tell, but we do have ways of going and sort of defining this. But what you end up seeing happens in type 3s is these 3 shotgun blasts lie along a line, okay? In other words, there's only one coordinate, which is the coordinate right along this direction, okay, that goes and separates these particular clusters. And what are we trying to do? We're trying to separate out these 3 clusters, but there's only one direction that matters, okay? And I'll talk about a second, what is this direction, okay? Well, it ends up being a half of a far and a half of a near. A half of a far and a half of a near means add the 2 together, take their average, which means full stack, okay? So for a type 3 that we tend to work with a lot, there's only one stack that matters in terms of discriminating all 3 of the things that you care about, and that's the full stack, okay? In that case, I say AVO doesn't matter. Don't worry your pretty little head about it. Just go and look at your full stack, okay? Okay.
Just a point, Mike. I know I've been out for a while, but I suppose strictly speaking, it's not really you can have in that lower left quadrant both a type 3 or a type 4 amplitude response. So you can have a class 4 where you have a soft event that is bright on the nears and softens with offset.
Well,
I mean, if it was a gradient intercept display, I think that would be right, but in terms of a near versus far.
That is correct, yeah. And I was actually, it's really, they talk about it in terms of where it falls on the gradient intercept plot, you know, as such. And you're right, there is a particular linear transformation between the two. You're right. But also I want to go and point out, though, too, some of the particular confusion that people also get is that if you go and focus on the middle of these clusters and say, this is what I end up expecting for one of my brine sands, what happens right here, okay? Some of these cases actually go and have a dramatically different sort of class behavior, but it's because there's overall a particular spread amongst these particular, you know, that it's not a point, it's actually a cloud, and this cloud can actually straddle what you'd identify as different behaviors, okay? So that even though, again, I caution you, even though a person may say the center is here, that doesn't mean that you aren't going to find some other particular points that are in another quadrant, okay? But now let me go and talk about the cases where AVO does matter. The North Sea, hard sands, okay, is a well-known area where AVO matters. These are what the shotgun plots look like for the North Sea. One thing that you notice, and this came from what Dave was saying, when you do Gaussman substitution, it always takes this cloud and moves it in the same direction. So the orientation of these 2 sort of shotgun blasts will always be the same. And you see that's actually the case here, that the orientation of those 2 shotgun blasts are the same. But you also see that these 2 particular blasts have been actually rotated around in this direction as we've gone over to a particular hard sand geometry. Why do we call that a hard sand geometry? Well, if you look at the center of the brine sand, it ends up being hard on both the near and the far, but obviously it's going to be even harder on the farther over this way, than the near, okay? And that's, but also notice another thing, that this particular cloud also has a lot below the line, so that it actually could be a negative on the near, but then switch sign on the far, so it could polarity flip. It could be a positive that gets brighter, okay? And, you know, there are also even another one over here that's a negative that gets, you know, a little bit dimmer, okay? Even though that ends up being fairly unlikely. And also notice another thing about the structure here, which ends up being distinctly different. You have three clouds that no longer form a line, they form a triangle, okay? And what this means is if I want to go and tell the difference between a brine and a hydrocarbon, if I know it's sand, I want to look along this direction. And if I want to go and tell the difference between a shale and a sand, I want to look along this direction. They end up being perpendicular to each other, okay? And many times you would end up talking about the background normal goes in this direction in this case, but you end up finding that it ends up being along this direction, you end up getting the best lithology sort of separation. Normally, the equivalent of the background normal in this direction ends up being along this direction, okay? And so this is really the fundamental difference of when you need two numbers, because now you can actually separate and you get better separation using two numbers rather than one number because you don't have a degeneracy associated with it, okay? And now let me go and sort of talk about this space and sort of, before I go and sort of talk about that space a little bit more, you'll say, well, you're using near far rather than L and M. Well, you can go in and write that the near stack is going to be L plus M sine of theta 1, where theta 1 is a small angle. The far stack is L plus M sine squared theta, where theta squared is a big angle. You can actually go and invert this relationship in terms of the near and far now as a function of L and M. It's a little 2x2 linear transformation. And you can go and invert it that if you know near and far, there's actually a simple linear transformation in order to get L and M, okay? So they end up being sort of effectively sort of the same, or there's always there's a simple linear transformation that ends up separating the two, okay? Now you're going to ask me, okay, why, okay, it's a little bit like those two numbers, you know, that we were talking about before in terms of, you know, do I use, you know, Young's modulus or the bulk modulus or lambda mu and the like? Well, first of all, we end up using sort of relative numbers here, so it's going to be L and M or N and F, so we're really looking at delta changes rather than absolute changes. That's one thing that's kind of VHP centric. But why would you want to go and use, let's say, near and far rather than L and M? This is a paper that was presented at the SEG about 6 years ago now by Solid. And I sort of posed a question to you earlier of what would make a difference between coordinates, okay? What do you think the answer sort of is to that? Does anyone have a thought or? Okay. Well, it's actually a very profound question. And really what you're trying to do is separate clusters. You're trying to separate clusters, and you'd like to be able to separate in a way that's independent of the noise that you would put on it. And it turns out that these directions end up being noise dependent, or there's a background normal rotation that ends up coming about, okay, due to the amount of noise that you have put on it. And it's very unsatisfying to have your coordinates change as you increase the noise level as you move around the data, okay? And it turns out that the property that you want to have are what are called orthogonal stacks in order to have the noise not matter, okay? And what do we mean by the orthogonal stack? If you look at the weights that make the stack, if you multiply them together and then sum them together, they should equal 0, okay? For instance, a near and far stack. A near has 1s all the way out to some offset, and then 0s after that. And far is just the opposite. So if you multiply them together, you always have a 0. You sum a bunch of zeros together, right? Okay. What's the stack that's orthogonal to the gradient stack, okay, which is an M stack, okay? What do you think it would be? That ends up being the full stack. Because a full stack has all ones. A gradient stack starts with a large value, goes through 0, and then has negative, is symmetric. So if you multiply everything out and add them together, it ends up giving you 0. Okay? Those are particular orthogonal stacks, and you find that what you normally want to do, and another way of looking at it, is you want to do a principal component analysis. Those principal components will always necessarily come out to be orthogonal directions in terms of these stack combinations. And if you go and look at these things, normally the first thing to come out is something fairly close to a full stack. The second thing is something close to a gradient stack. But if you're going to go and try to understand where things are in sort of a two-coordinate space, you like to balance out those two first eigenvalues a little bit better. And to balance them out, you like to go to sort of a near and far. Okay? So you, instead of looking at L and M space, you should be looking at sort of M and full stack space, or looking at something like near and far space in order to get sort of the optimum separation. And so it's sort of that paper, and it's in the references, and I would highly suggest that you read it. It even has a justification of why when you do these stacks you always taper them. Actually, that even comes out in the theory of how you should be tapering these stacks. And it's informed the choice of why we look at near and far stacks. But it also ends up helping in terms of an interpretation of what I call all types of sort of rotated stacks. And if you look at the near and far stack and the different directions and the possible coordinate rotations that you can make in this, there starts to become a very easy interpretation of that. And let's set it up by saying it's near times cosine theta plus far times sine theta, where theta is the amount that we rotate our coordinates, okay? And this is actually something that Guy pointed out and really ended up being, I think, quite useful, is that as you start going, and we start with a near stack, which is 0 degrees, if we go out to 45 degrees, we end up getting near plus far, which is equal to a full stack. And then if we go out to 90 degrees, we get a far stack, okay? But it gets kind of interesting. If we start then going past the normal, that you end up finding that you end up getting a near minus far as soon as we go, what would be, 90 plus 45, which is 135 degrees. We end up finding we get what's effectively a gradient stack. And then if we continue back on, we end up coming back to the near stack when we end up reaching 180 degrees. And so now we have a continuous way of sort of scanning between near to full to far to gradient and back to near stack as we kind of spin around. Yeah, you had a question?
Well, on the assumption that the nears and fars line up such that you can do some math between the two cubes of data.
Yeah, well, we also will talk about that we actually go, and if you go and extract the amplitude separately on the near and far and allow sort of a readjustment, take those two amplitudes, you can actually do amplitude map manipulations that can sort of effectively align the data for you. But you are right that if you actually do these different stacks, that you need to make sure that the data is well aligned and there isn't, a significant amount of residual move out associated with it. But also, if you get into the issue, if there's actually differential AVO, sort of causing some of this stuff to happen, that's probably sort of something best left to when we talk about in lecture 12 on this. But that does go, yeah. But I think that what we're really talking about here is event math, where we've sort of snapped it to where the peak is, okay? And the particular thing, and this was really, I think, quite an interesting thing that Guy came up with, was if you look at what the separation is, or the amount that you can boost, let's say a brine sand versus a shale, or a particular oil, or a brine sand versus an oil sand, which is kind of a fluid, or an oil versus a gas. And so the big thing is to look at the difference between the black and the two colors here. Is you see that if you have one of these type 3s, that everything sort of goes up and down together, and you find that you get kind of a broad maximum centered around where the full stack is in terms of your ability to separate those peaks, with the fluid, the oil and the gas being the easiest thing to particularly separate. But if you now go and look at what the things are with respect to the hard sand, that because these are a triangle, you start seeing things sort of go out of phase, where the optimum stack associated with understanding a brine sand from a shale now tends to be something like a near. And then if you come out here to the, try to tell the fluids apart, that you like coming out much closer to a far stack, okay? And in fact, if you really wanted to go and just be able to tell what the fluids are and have no difference between whether or not you're a sand and a shale, you probably want to even come out here a little bit further. Well, actually, you do want to be around the far stack. But if you wanted to go and eliminate differences between the fluids and only be able to see the difference between sands and shales, you actually want to come back here an angle a little bit to one of these gradient stacks to where we really can see the difference between sands and shales, but there's no difference between where the hydrocarbons are, okay? And in fact, if you go, and for those of you who've sort of heard the concepts of elastic impedance and what is, sort of extended elastic impedance, that what we really are talking about here is extended elastic impedance, because what BP did at first was had near plus far times tangent theta. They realized that there was a particular discontinuity when we ended up coming up to theta equals 90 degrees, and they never could easily and continuously map things back to negative angles. So they multiplied by cosine theta in order to eliminate that, so they could easily go back to these angles. Why was BP interested in? Well, they're big players in the North Sea. And lo and behold, you find that the particular angles, to really be able to follow the continuity of the reflectors, up dip, down dip, and be able to figure out your volumes, ends up being some of these sort of close to gradient stacks, which actually have to go back into some of the negative angles, or go through that particular discontinuity, which would happen in the tangent at this location. And even if you try to go around the other way, you would hit the discontinuity here before you get to here. So this is kind of blocked off by discontinuities from you. And that's really what sort of brought them in to look at this. But you ask sort of, why would you want one of these particular stacks? Well, if you go and take a look at this carefully, that what you end up finding many times is that you go from sort of a nice hard reflector down dip, and many times this moves around even more, and you end up having your sort of up dip, especially oil sands, can effectively have no reflectivity, okay? So what you'll see is a nice hard brine reflector, and then you'll see the whole top just chopped off of your prospect and you can't see it at all. Well, that's great for knowing there's fluid there, but how do you know how much sand is there? There's nothing, okay? So you want to have some way of restoring what, was at that position. And so you want to go and get to one of these particular, what are called lithology directions. And to give you an idea of what that looks like, is that, in this case, you end up seeing that there ends up, it's sort of the opposite case, of where there's a nice bright reflector that ends up disappearing down dip. But if you now go, that's the fluid direction, but if you'd actually go and rotate this into the lithology direction, you end up seeing much more distinct lithology sort of down dip, where you can go and understand, what the particular structure is in one of these sort of transparent legs. I know this has probably been, I said it is sort of the advanced sort of amplitude analysis, but since it was that's sort of the name of the course, and fortunately or unfortunately, we're going to go and have been getting into that. But now we're going to get into, I think, probably one of the more complicated things, which is how do you relate these measurements in millivolts on the near and far stacks to the modeled responses that you would, expect to get, okay? And that we can go and extract the amplitudes on the near and far stacks. In fact, we go and we see two particular clusters here, okay? And, Dave showed sort of the modeled versus actual, and sort of went and sort of calculated that particular coefficient, okay? Well, he was going from a one-dimensional scalar, a scalar to a scalar, so one number is good enough, okay? But for us to be able to go from these particular measured amplitudes to what the reflection coefficients are, we actually have a two-component vector here. And we need to go and have the transformation ends up being a 2x2 matrix in order to be able to go between the two, okay? And what you end up finding when you take a look at this is if you went and did one of these matches, that you end up seeing that there's sort of a wavelet that will go and sort of map, or a coefficient that maps sort of the near stack to the sort of the near reflection coefficient, and that ends up being a particular number. And also, normally, because the near stack is so close to normal incidence, that theta is, and especially sine squared theta, is so close to 0 that this number normally does not matter. But then there's also a coefficient associated with the scaling of the far data, and another particular coefficient that has to do with that B factor that I sort of talked about in the AVO response, which is the ratio of the effective angle to what the theoretical angle should be. And if you take a look at how these things go in terms of this transformation, that they end up going in that you have a near coefficient here, and you have the far coefficient here, and if B was 1, which is a theoretical value, you just have the far wavelet, which is the scaling coefficient. You have 0 here, but you end up getting a certain amount of sort of rotation starts coming in because of sort of non-zero B value, or you'll start seeing a rotation in these coordinates, or the orientation of these ellipses, as you start putting in a B factor that's sort of different than 1. But what's kind of interesting, and you'll see, is that if you go in and do one of these wavelet derivations, that you end up going and finding that if you plug in these numbers, then lo and behold, these things will transform fairly close to what or within the sort of theoretical sort of shotgun blast associated with each one of these two clusters. So you can end up doing a one-to-one correspondence. And so this is sort of how, if you end up having a well log, how you actually determine what this sort of 2x2 matrix is, okay? But and we'll actually have an exercise on this near the end of tomorrow, where though if you do not have this and have to sort of look at and sort of do the equivalent of background normalization, that we'll talk about the ways that you can come up with what these numbers are in sort of the absence of sort of the background normal. Be able to go and try to match these up and do the particular separations associated with it, okay? And that includes, defining the shale trend, for instance, can be one way to sort of help reference things, and then look at some differences from that. So, okay? I know there's sort of some blank looks. Are there particular parts of this, or are there particular questions that you may want to sort of form up, and I can sort of dig back into certain parts of this? Or mean, I think that, I mean, if I sort of go into the, summary, so of this, and let's see, well, we talk about the small angle, small contrast. Let me just get to the, I think the main stuff though in terms of the AVO, is that overall, you know, the thing is really good to remember is the difference between when AVO is important and not. When all three of those clusters are along a line, and when all three of those clusters are not along a line. Okay? The other thing is that you can pick many different coordinates, but really good coordinates to work in end up being near and far. And also that we can go and ask questions about sort of what are sort of the optimum directions for separating out lithology and the like. So if you have a triangle, sort of what are those sort of optimum directions? And if you have a well log, that you can really figure out sort of an absolute calibration so you can compare the two together. And there are some other ways of sort of figuring out what those particular calibrations are. Okay? John?
I was just thinking, the Zephyr slide we saw earlier, where it showed the P-wave reflection coefficient changing sign as you change angles, it kind of explains why this gradient thing might be useful in some of these cases. Because essentially you correct that sign, so you sum all of these things rather than summing them here and then subtracting.
Yeah. And also, if you ended up having the gradient stack, that would reinforce that behavior. Exactly. Yeah. And that's the reason why that ends up being the second stack. They find that the gradient stack is the best at figuring out what the gradient is.
So, but, like, is there any reason to choose these particular types of stacks? I mean, there's sort of an infinite amount of ways to generate orthogonal. Essentially, these are filter banks. You're applying them to.
Yeah. Well, you'd end up going in principal components and start picking them off by. You want them to be orthogonal, and you want to go and pick the things, the two largest eigenvalues. In a principal component search. Well, in fact, that's what that paper's about. So if you go and look at it, that it really talks about what's your choice. It's an infinite filter bank, and what's the optimum choice in order to do the discrimination.